so let's just kind of revisit. Last time we talked about lots about Boolean operations um, and particularly using those for conditional statements, so if then else, elif, that sort of thing. Um, and a little bit about more about the unit testing stuff, um, just for sake of example. And where we're going to use this, well, a number of ways, is to continue talking about loops. So just for way of reminder, let's look back at the first kind of loop construction that we did, which was something silly, right? Just printing uh, the numbers up to a given input number from the user, nothing particularly special. But what was the construct here? Right? We have a loop that's printing 1 through, in this case, 5. Um, and I had to do one extra on the end there because of the way the range thing works, right? Remember, it's closed on the left, open on the right. Okay. And you guys used a construct much like that in the um, the second mortgage or car loan calculator, right? Because what were you doing? You had each month's computation was in the body of the loop, and then you just looped over however many months there were, and then dealt with the last month separately because of the rounding issue. But that's essentially what you did. It was just a bit more fancy than this. Yeah. Okay. So the for loop is certainly not the only kind of loop we can do. And the for loop is a good one if you know in advance how many times the loop needs to run. So, for example, with the mortgage calculator or whatever, the user types in the number of, well, either years or months, depending on which way you access that, and then you convert it to months if necessary. And so even though like it's a variable value, once the user types in the specific number of months, it's now a fixed quantity. And it was, 60, I guess, in most of our example computations, although it obviously doesn't have to be 60 exactly, right? So you could use that same calculator for a home loan instead of a car loan. It's just going to be, most home loans are uh, either 15 or 30 years. Um, and the interest rate obviously is a little different than a car loan. Yeah. Okay. So, so if you know in advance how many times you want to do something, then a for loop is generally going to be the right construction. But what about if you don't necessarily know in advance how many things or how many times you want to loop? Well, the for loop sort of is designed on knowing how many times you want to loop. Okay, so there's another construct, and it's called the while loop. So just as a really cheesy example, um, so let's suppose that I have some number of slices of bread and some number of slices of cheese, uh, and I want to produce a bunch of sandwiches or grilled cheese sandwiches. Well, what is necessary to make a grilled cheese sandwich? Cheese and bread, okay? But in more detail, okay, yes, you also need the butter and a hot skillet and yeah, exactly. You need two slices of bread for each slice of cheese, because that's, I guess, the definition of a sandwich, right? It's not a sandwich if you only have one slice of bread. Yes? Well, okay, but then, yeah, I mean, we could argue for the next hour about what the true definition of a sandwich is. And by the way, a hot dog is not a sandwich. I don't care what any of you people say. Okay, yes, it's a taco. That's okay, fair, yeah. Uh, Yeah, is a I don't know, is a stuffed crust pizza a sandwich? Or is a, you know, where it's got crust on both the bottom and the top? Yeah, is that a sandwich? Well, no. Okay, anyway, um, joking aside, right? So let's suppose, right, we need obviously two slices of bread and one slice of cheese to produce the sandwich. Um, and in this case, like we could calculate how many sandwiches can I make given what I've got here. Like just given the numbers I picked, we can make how many sandwiches? Seven. Okay, but we may not necessarily know that in advance, or it may not be quite so obvious um, in other situations. Okay, so let me just say print making grilled cheese sandwich. Okay, and then what do we need to do to our variables here? If I make a grilled cheese sandwich, then what have I done? Yeah, I've taken two. Um, I need to subtract 2 from the number of slices of bread and subtract 1 from the number of slices of cheese, okay? And I've written it this way because, or typed it this way, just to show you another way that you can do it, that probably the default that you would have guessed is num bread or num slices bread equals num slices bread minus 2, okay? This is equivalent, and obviously this is shorter, right? And deducting 1 or 2 or something, or adding 1 or 2 to variables is such a common thing that we do that it's kind of nice to have this shorthand for it. Um, yeah. Okay. So is that okay? All right. I didn't have to do it that way, but I just did for giggles. Okay. And then yeah, go ahead, Thomas. Uh, yes. And if you did that, then the value of the other variable would be what gets subtracted, right? So it doesn't have to be a constant number on the right-hand side, although in this case that makes sense for our example. Yeah. Okay, and then so what should we do when we finally run out of everything? Let's just print all done. Um, all done, and then we could also say print remaining bread num slices bread, and then slices, and then we could print remaining cheese, num slices cheese, slices. Okay. Again, cheesy example. I just want to kind of start. Okay, so when the condition here, right, is this loop is going to continue executing over and over and over again, uh, as long as the condition, the Boolean condition inside the parentheses there is still true. Okay, um, and that so for example, what would happen if I had forgotten to deduct 2 from the number of slices of bread or the numbers 1 from the number of slices of cheese? Yeah, I'd be making sandwiches forever, or rather the loop would continue forever. Okay, now that's obviously not realistic here for our sandwich example, but it would be realistic for some programs. So actually a good example would be the turtle program, right? So the turtle program, the screen is still there sitting, and so technically something is still running until you actually close it, okay? Or your video game, while exit is not true, just keep running the game, right? So your game is inside a giant loop, basically. Okay, so is that all right? Um, And so having a loop that basically goes on forever is not the end of the world, but it may or may not be what you want to do in some situations. Okay. Okay, so we'll deduct 2 from the number of bread, the 1 from the number of cheese, and then at the end of the loop, right, so after we execute line 8, it's going to go back up to line 5 and check, okay, now what's true? Is the number of slices of bread greater than 1 and the number of slices of cheese greater than 0? Well, that could now be false, just depends, right? And in this case, which one is going to become false first? We'll run out of cheese before we run out of bread. But so the right-hand part, the numbered slices of cheese, that part will become false first, but then once it's false, the whole statement is false. And then we won't execute the loop body anymore, and we'll skip down to line 9 or 10, basically, whatever's after the loop. Okay, so does that make sense? The other thing is about the while loop construction is that condition gets checked before you do anything at all. What this means is it's possible that a while loop runs not at all. Okay, so for example, if I change my number of slices of bread and cheese to 0, would I make any sandwiches? No, okay, because the condition of having more than 1 slice of bread and more than 0 slices of cheese was never true, and so I'm not going to try and make a sandwich, right? So the condition gets checked first. In some languages, there is another version of the while loop called a do while loop where you check the condition at the end rather than at the beginning. But the while loop checks it at the beginning, not at the end, okay? Okay, so is that cool? What on earth is going on out there? People having too much fun. They're playing games. Okay, so let's run this, of course, and see what happens. And what should happen? How many sandwiches are we going to make? 7 in this case, right? So 7 sandwiches, all done. We are left with 6 slices of bread and 0 slices of cheese. And since we knew the numbers in advance, that jives, right? Everything looks good. Okay, so does that make sense? Yeah. So kind of like a for loop, except we don't necessarily know how many times it's going to iterate. And if the condition here is something that's really complicated, like in this case, we're not idiots, right? We could realize that 7 slices of cheese, 20 slices of bread, we're going to make 7 sandwiches. But if it's a more complicated statement, it might take more brain power to figure that out. And it may not be worth figuring it out. Okay. Okay, good. So what we can do with this, for example, is, well, any questions actually before I move on? We'll do kind of a fun example. No? Okay, so let me make a thing here, and I'm going to call it colats, okay, for a reason. And so what I'm going to do is I'm going to define a function of a number. And this number, I'm going to do the following. If the number is even, could one of you shut the door, please? Okay. So that's it for my function. So it's going to accept a number, and if that number is even, then it's going to divide it by 2. And if that number is odd, which would be not being even, right, it's going to multiply it by 3 and add 1. Okay? And it probably at this moment seems like I'm just picking, like, why on earth would I define such a function? Has anybody actually seen this function or heard of this problem before? Okay, Thomas has. Anybody else? Okay, so Thomas, keep your mouth shut, because I don't want to spoil it. Yeah. Okay, so what I'd like to do is I'd like to run this on a given number. Okay, so let's just say my num equals int of input. Please type a positive integer. Okay, so I'm going to take an integer from the user, okay, and I'll just call it my num. And then what I'm going to do is while my num is not equal to 1, or equivalently, I could say while it's greater than 0, or actually greater than 1, I'll do that. Okay, so while the number is greater than 1, I'm going to basically pipe it back through the function to get a new number, and then I'm going to print the number that I get. So I'll start with whatever number the user types. Okay, so like if I type 5, in fact, why don't we go ahead and print that too while we're at it. Let's print it here. Right, so let's print the number that the user gives us. Then in the loop, we'll update the number and print the new value, and then continue this process as long as the number that we've got is bigger than 1. And then once that's no longer true, if our number ever gets less than 1, or sorry, less than or equal to 1, then we'll terminate the loop and just print the final number. Now, if I start with a positive integer, can I ever get 0 out of this function? No, okay, because 3n plus 1, what does that do to a number? It always makes it bigger, right? So what's the only way that the number can get smaller here? Is if it's even, okay? And if the number ends up happening to be 2, then I divide 2 by 2 and of course get 1, and then I no longer will be in the loop, okay? All right, make sense? Okay, so let's run it. All right, please type a positive integer. Any suggestions from the floor? 7? Okay, so Mark said 7. I did hit enter, didn't I? Oops, okay. All right, what did I mess up, guys? Type error. Greater than is not supported in specific instances of num type and... Yeah, my num should be an integer, right? Well, let's do... Huh, that's interesting. It's class int, but then why does this not work? Am I being an idiot this morning, guys? But my num, but it does, right? Okay, you know what? Let's just do this for right now. Let's just, instead of accepting user input, let's just hard code the number, and I'll figure out why I'm what I'm doing wrong later. What? Oh, hold on. That doesn't make any sense whatsoever. Okay, you know what? Um, let's do this. While it's not true that the number is equal to 1. Okay. Sorry, it's complaining about the division here. Okay, do I need to use the math package? Um, maybe that's what I need. Nope. Because percent is the remainder operator, right? Oh, okay. Maybe I need to put actually a set of parentheses here. Sometimes that. No, okay. Why is that doing? Oh, because, okay, yeah. So what I would want to do then is, well, I could say int of n. I really don't want to say it that way, but no, and I can't really do that. Okay. Oh, thank you. That's what I forgot. Thank you. Okay. So yeah, we never returned a value. And so down here, when it's saying num equals colats of num, there we go. Okay. So it does help to not be an idiot. Okay. So let's put back in our user input. So one of the things that you probably, or that just teaches us, by the way, is that Python's errors and the messages it displays when you get an error are not always very helpful, right? Um, okay, there we go. That's better. So yeah, my function never returned a value. That's the mistake. And so it was trying to, after it ran the function once and nothing got returned, now this variable has none type because nothing, it doesn't exist anymore. And yeah, okay, that makes sense. Okay, so let's type a positive integer. Let's do 7. Okay, so 7 is odd. So multiply it by 3 and add 1, I get 22. That's even. Divide, get 11. Then 34, 17, 52, 26, 13, 40, 20, 10, 5, 16, up, and now 8, 4, 2, 1, 1. Okay. Um, and so let me actually just change this back to what I had before. Okay. So what do you notice about the, and actually I don't need to print it a second time because it prints after we recompute. All right, let's pick another number. This is a number apparently that you guys like. Okay. So what do you notice? Okay, it always seems to come back to 1. Yeah? Um, and you can try it for whatever other numbers you wanted. In fact, we could throw this whole thing in a for loop and try it for every number from 1 to whatever. Okay, and so here's sort of an interesting question. Does, if you start with any positive integer and you go through this procedure, will it always eventually hit 1? Nobody knows. Everything we've tested it on works, right? And we've tested it on a lot of numbers, right? But how do I know that like 1 googolplex plus 7 won't actually work? I don't. I mean, I could test it, right? So I called this function Collatz because this is actually an interesting math problem. It's called the Collatz conjecture, and it is unknown if this function will always eventually hit 1 for a given input. We just don't know. Even though, like I said, we've tested it on a gajillion numbers. Okay. Well, yeah, I mean, nobody's been able to prove it, right? Because, see, here's the thing. Can we test every number? No, that's not possible. There's infinitely many of them, right? So we could test it and say, yeah, it's true up to 10 billion or 10 trillion or whatever, right? Uh, and just stick a supercomputer on it. But we don't know the general answer. It's still an open problem in mathematics, which is kind of neat. And that's not a very complicated looking function, right? So yeah, nobody knows. Okay. Kind of cool. All right, so another thing that I'll show you, and actually the book has this example in it, and also the next one I want to show you. And I'm really glad it does have it in there because I think they're really cool, and I like showing these anyway. Um, don't think that I'm being too lazy here with my examples. So here's another question. How can I compute the square root of a number in Python? Yeah. Yeah, math.square root, import the math package, and bam, it'll spit something back out. Okay, how can you compute the square root in Python without doing that? Okay, yeah, you could raise it to the 1/2 power. Okay, that's the same thing, really, though. Okay, without doing that either. Okay, and let me make it spicier. Not using the math library at all. Just using multiplication, division, addition, and subtraction. Yes. Yeah, they are, but okay, let me back up, right? Um, no exponents either. Okay. Right, you're out in the wild and you don't have anything. So yeah, this may seem like a contrived thing, but let me sort of tell you a story as to why you would need to be able to do this. Um, when Python is computing floating point arithmetic, it's doing it on a floating point chip, right? It's passing this to the processor. The processor has on board the capability of doing floating point arithmetic. That was not always true. Okay, so for example, my favorite old computer sitting here, my good old Commodore, does not have a floating point processor on it. It can only do integer arithmetic. Okay, and so if you wanted to compute square roots, you would have to figure out a way of doing it only with the things that that machine was capable of. And that meant doing integer addition, subtraction, multiplication, and division. Oh, and by the way, it couldn't even do hardware multiplication for integers. You had to do that in software too. But it's a chip from the late 70s, so okay, we shouldn't expect that it has everything on board. Modern processors do. They can do floating point just as well as they can do integer. In fact, you guys know AMD, right? The chip manufacturer, right? They got their start back in the day by actually making floating point coprocessors and underselling Intel's coprocessors. And then as they grew as a company, then they started making their own processors, and then they bought the ATI, which is the company that made the Radeon graphics cards. They bought that many, many years ago and sort of incorporated it into the AMD umbrella. But yeah, back in the day, you'd have to have a separate processor just to do all the math stuff. Okay, so let's sort of deliberately tie one hand behind our back and see if we can come up with a way of doing square roots without actually doing square roots. Okay, make sense? All right, so let me illustrate the idea of this on the iPad, just sketch it out, and then we'll program it. So the other reason that I want to show you guys this example is because this technique is actually ancient. Um, And hold on, I think, yeah. This technique is ancient, meaning, in this case, how ancient? Anybody happen to know where I'm going to go when I say ancient today? 15 years. In the computer world, that's relatively a good answer. Yeah. Fair. Okay. It's even older than that. Okay. So this technique is from Mesopotamia. Right? And it's an ancient, like I said, method of computing square roots without actually computing square roots. Okay. So suppose I want to compute the square root of 2. Okay, and I'm just going to pick the square root of 2 as a nice example because it's something whose square root we happen to remember the decimal digits for. It's right 1.14 or 1.414 blah blah blah. Okay, and it comes up in trigonometry. If you've got a square with 1 units on each side, then how long is the diagonal of it? It's the square root of 2. So this is a useful number for sake of example. But I can do this for any value. It doesn't have to be the square root of 2. Okay, so one of the techniques that we use often in mathematics is make a guess as to the value and then improve the guess. And if you improve the guess, well, then you can improve that further, and you can keep improving and improving until you get whatever accuracy you desire for the problem. So, for example, if we did this once and we got 1.4, is that good enough? Maybe, right? Or is 1.41 good enough? Maybe, right? So how accurate do you want it? Or maybe better put, how accurate do you need it? It's up to you, okay? So let's make a guess as to what this is going to be. So guess, and I'm going to call this X naught, and somebody give me a guess. Now we happen to know the true answer here, so give me a reasonable guess that a non-moron would be able to have figured out. 1.5 seems reasonable, right? We know it's going to be a little bit too big because if you square 1.5, what do you get? Which is bigger than 2, right? So we know it's not a great guess, but it's certainly not as bad as guessing 2. Okay? All right, so let's guess 1.5. Okay, so what I'm going to do is I'm going to compute this. All right, now you all got phones in front of you, so pull them out and calculate. I want 2 over 1.5 plus 1.5 all over 2. 1.417, Thomas says. Now, would you guys agree that that is better than what we started with? Yeah, we're already correct to 2 decimal places, right? The third one's off a little bit, but for one pass through this function, that's not so bad, is it? Okay. All right, well, let's do it one more time, shall we? So it'll be 2 over 1.417 plus 1.417, and then we're going to average those two numbers. Okay, and so what did you get? 1.41421. Okay, that's pretty dang good. Yeah? Okay, so what am I doing here each time I wrote the word compute? I'm basically doing the exact same thing, but with a different number, the result of the previous computation. Well, what's that code for, gentlemen? A loop. right? So if I want to program this, I'm going to do a freaking loop, because that's what I'm doing here. Now, we have to decide under what circumstances should we stop the loop. Well, we got a couple of options. If we did this with a for loop, we could say, you know what? It seems to be working pretty damn well after 2 passes of this. So maybe if I write a loop that just does it 10 times, that'll be good enough. Okay. Or I could try and come up with some sort of condition. Like in the case, for example, of the square root of 2, do we know actually the digits out to however far we ever wanted? I mean, we could compute it like over on the side, and we could say, all right, as long as I'm within, it's correct to the 5th decimal place, then I'll call that a win, and we'll quit then. Okay. So to start programming, at least initially, let's just do it for a specific number of times, and we'll see how good the numbers start getting. And then we might say, you know what, maybe 10 times was overkill, maybe only 5 was necessary. Okay. Is that okay? Okay, so there's one other thing I want to point out here, and I probably shouldn't have picked 2 as my example. So the division that I do here, that is always the number 2. The numerator there is the number you want to square root. Okay, so if I wanted to do the square root of 3, for example, I would have 3 up in the numerator, but still 2 in the denominator. Okay, is that all right? So I really shouldn't have picked 2 for the example. Okay, so good. All right, so let's program it. All right, so let's call this square root. Okay. And let me actually make a function that does what we wrote out just to sort of modularize it. So I'm going to def magic function, and this is going to take in a number. Okay, and what do we do with this number? Yeah, we are going to divide. Actually, you know what? I'm going to do this. I'm going to define it in two things, N and S. So here I'm thinking N is an approximation of the square root of S. Okay. And so what I'm going to return is I'm going to return N plus S over N divided by 2. Okay. So in the case of if I'm trying to do square roots, what's S? So the example we worked out on the iPad, what's S here? 2. And what is N on the iPad example? What did N start as? 1.5. And then it became 1.417 and so on. Okay, does that make sense? Okay, so then in my main program, let's write a loop. Let's do it 10 times. Okay, what do we want our initial guess to be? Let's just say it's 1.5. Okay, and what do I want to do here? I want to compute initial guess equals magic func of initial guess and 2 in this case, because I'm doing square roots of square root of 2. And then I'll print the initial. You know what? Let me just shorten this to guess, just so it's a little bit more readable. Okay, good. And then when we're all finished, Well, let's actually, I'm going to do this. I'm going to go ahead and import math. And then just for the sake of comparing how good our answer is, let me just do that. So this way we can compare uh, how good our computations are against the actual value, or that's as many decimal places as Python can do. Yes. Oh, sure. Yeah, and I can add that later. For now, I'll just say that we're definitely doing the square root of two, right? Just for the sake of comparing it to what we already did on paper. Okay, so does that make sense? We're just gonna make a guess, print it, print the basically as exact as Python can make it, and then we'll go through our loop and print it however many times just and see what happens. Yeah. Okay, good question. So the reason I'm putting the print statement, so the question is why do I have the print statement in the loop? It's going to adjust the guess each time. Yeah, if you want to, right? I mean, you can, because what the loop will do is actually print each subsequent approximation. And because I'm printing every time I go through the loop, right? So the loop is actually going to print out like, well, 10 different answers, and they're going to get progressively better as we go down. If you want to put the exact answer down at the bottom instead of the top, I mean, that doesn't really matter. That's up to, that's like, what color curtains do you want in your bedroom, right? Um, yeah, good. Okay, so let's run it and see what we get. Survey says, all right, let me move this up a little bit so we can see more. Okay, so our guess was 1.5, right? And Python, using the built-in math library, gave us that approximation correct to whatever, how many decimal places is that, like um, 15 or so, roughly, whatever. And then looking at what our function pipes out, how many iterations did we need before it basically matches the quote exact value? We didn't need 10. We really only needed 4, right? Because these numbers from number 4 down don't change. Okay. Now, they strictly, like mathematically, they do change. It's just that Python and any computer is only capable of doing arithmetic to some degree of precision within the hardware. And Python, I think, defaults to probably 64-bit floats, which is, I mean, like that's the precision NASA uses for sending space probes to other planets. Okay, so like if it's good enough for getting space probes to Pluto, which I guess got demoted from being a planet, um, but when I was a kid, it was a planet. Um, yeah, yeah. In fact, when I was a kid, it was actually the eighth planet, not the ninth planet. How is that possible? Do you guys know? No, it. I'm not that old. Okay. No, we knew about Neptune, but Neptune was number 9 at the time. Yeah, their orbits cross. Okay, so yeah, their orbit. Pluto is in a really eccentric orbit, and it actually crosses inside of the orbit of Neptune for part of its orbit, and they're in a 3-to-2 resonance, so they'll never actually crash into each other. So, which, yeah, would be pretty cool, actually, if that happened. Possibly, yes. Actually, probably not, because Pluto's not that big, and Neptune is a gas giant, so there's not going to be like it's not a hard object versus hard object collision. It's a hard object versus a big ball of gas, right? With a hard object in the middle, but the Pluto won't last that long, right? What we would get is a nice ring around Pluto, probably, would be what would happen. Yeah. So, anyway, um, actually, that could be a fun thing to do with turtles is to make planet simulators, right? You need to know a lot more math, sadly, but yeah, because turns out orbital mechanics is a little complicated. Uh, okay, so um, only 4 iterations of this seemed required. Now, that was partly because we made a pretty good guess from the get-go of being 1.5. Like, if I had chosen a really, really crappy value, it might have taken a little longer before we started to get the accuracy that we're seeing here. So this is sensitive to the input values that you're picking. Okay. Yeah. So this technique, like I said, there are ancient Mesopotamian, from Babylon, clay tablets that basically describe this method. Okay. So that's really cool. Now, here's what's really cool. How many of you guys have taken Calc 1 or 2? Okay. How many of you guys have ever heard of a thing called Newton's method? Yeah. If you apply Newton's method to this question, guess what formula you get? Exactly that. Okay. So this is actually an instance of Newton's method that was discovered several thousand years before Newton was born. Okay. Newton's method is a more general technique, and there's lots of other crazy techniques for doing numeric approximation of stuff. Okay. So, yeah. Now, this isn't a calculus class, otherwise I'd go through the derivation to prove to you that this is, in fact, the result of doing Newton's method. If anybody's curious about that, ask me after class. I'd be happy to show you. Okay. All right, so any questions about this? Um, but essentially what were we doing here, right? We defined a function and we were iterating it. And we were, in this case, we said, all right, iterating it a fixed number of times is probably the better way to go instead of doing it basically continuously until some condition was true or false. And yeah, is it possible to convert any for loop into a while loop? Yes. Is it possible to convert any while loop into a for loop? No. Also, yes, but it takes a little bit more brain power. Okay. So you don't actually have to have both constructions. You can always build one out of the other. It's easier to build a for loop out of a while loop than the other direction, but it is possible to do that. So, yeah. Okay. So, question, preguntas, fragen. And what's the other thing that we've sort of repeated a few times today? Hmm? Well, functions, right? And it helps when your professor remembers to return values from functions that need to return things. Oops. Okay, good. All right. So the next thing I wanted to do, well, 2 things. Let's revisit one of the questions or one of the issues that you guys perhaps noticed in the mortgage calculator, which is what happens if your user gives you bad input? Okay, so what do we mean by bad input in the case of the mortgage calculator? Yeah. Yeah, so like let's say you ask for the interest rate and they type in Q. Okay, not particularly helpful, right? Or let's say that you're asking for a letter and they type in a number, or they type in a capital letter when you want a lowercase letter or something like that, okay? So what you can do is you can use loops here, particularly the while loop, as a way to do input validation, okay? So what would happen right now if we took inputs and we like we ask for a number and the user types in Q? What's going to happen? Probably going to give some sort of error, okay? But what we could do is say, all right, while the input is invalid, get an input. And the first time, then we just have to understand that the input is automatically invalid before the user has given it to us because there's nothing there yet, right? So we could ask the user for input and then check, is it of the appropriate data type or the appropriate value? And if it is, great. And if it isn't, reprompt the user and keep reprompting them until they give you valid information, okay? Okay, rather than having your program just quit. Okay, so does that kind of make sense? So, for example, in the mortgage calculator, what were valid numbers to be putting in, or valid inputs? They were all numbers in that case, okay? And can we tell whether or not the thing that the user gives us is actually a number? Well, we can look at its type, right? Or we convert it from string to int or something, okay? But then what are numbers that the user could type in that are numbers but are garbage for the calculator? Negative numbers for basically anything, right? Wouldn't make sense. And also numbers that are, well, let's say 0 wouldn't make a whole lot of sense. Yes, because if they're typing a string, they actually could put the slash there, in which case that's not something that's convertible to a number because it's a string with a symbol in it. You would have to process it like a calculator would first, okay? So yeah, if they did something like that, right? So we can check then with a loop, is the value an appropriate value? And if it is, great, move on. And if it isn't, just reprompt the user. Okay, does that make sense? Right. So input validation is a useful thing you can do with a loop. And the while loop would be good. Like basically, while the value is bad, just keep looping until finally they're going to give you a correct something that's a valid thing. Yeah. Okay. All right. The next thing I want to do, I need to switch over to my computer for it because I haven't installed the libraries on my Pi yet to do this. And for this part of it, I'm just going to show you from the book, which is one of the cool examples they give here. Oh, sorry, one other thing, I'll do this. We kind of pre-saged this with our tables. What did you guys realize with the mortgage calculator? You printed a bunch of stuff and it kind of looked like crap. Yeah. Well, how can you make the table look less like crap? You can do stuff like using a \t as part of a string. That's the tab character. And so you can space things out a little bit more. If you want to spend hours making a really cool looking table, you can do it. There's packages that can do it. So for the mortgage calculator, I deliberately said nothing about how to make the table look. I just wanted you to print stuff. Because then what did you all realize? Well, yeah, I printed some stuff, but it looks like crap, right? And maybe I'd have to do extra work to make it not look like crap, right? This is, inductive learning, right? Okay. So I just wanted to mention that that you, with not too much trouble, you can slightly make your tables look a little bit better. But there are some packages that allow you to make like really beautiful tables, color coded and all kinds of stuff, right? So you can go nuts with that. That wasn't the point of the assignment. Okay. The next thing I want to do, though, is to talk about a little bit about image processing, because this is a sort of common reason that you might, well, that you'll need to do loops, and in fact nested loops. So if I put a for loop inside of a for loop, let's say that I have something that's like for I in range 0 to 10, for j in range 0 to 10, do stuff. How many times will do stuff be executed if I do it, write it that way? A lot, but how many a lot? If both of them are range 0 to 10, and I'm just picking that, it'd be 100 times, right? The outer loop runs 10 times, and for each run of the outer loop, the inner loop runs itself 10 times, and 10 times 10, last time I checked, was in fact 100, okay? So if you nest for loops, or while loops for that matter, be careful, because the number of iterations is going to just explode when you do that. Okay. However, there are situations where you do need to iterate over two variables instead of just one. And a very easy example is in image processing. Okay. So how are images stored in a data file or something? What is an image? Yeah, it's a bunch of pixels. Okay. And so I can think of an image as being a two-dimensional data structure that has some size. Okay, so say for example, my picture could be, well, like what's the resolution of, say, the projector here? It's 1920 by 1080, right? So I'm projecting that many pixels up onto the screens, and maybe a little picture that, like, I don't know, I'm putting in my email signature or something, right, is smaller. But what is it? It's still just a grid of pixels. Okay. And if I want to do something with that grid of pixels, well, then I need to iterate over the row and the column number for that image. Okay. So images are stored basically like this. The image has some width, it has some height, and where is the 0,0th entry? Which pixel does that correspond to? By convention, it's the top left pixel. Okay. And then as I move to the right, I'm going across in my column, and as I go down, I'm going across in my row, and every pixel is one of these dudes. It's row number something, column number something else. Yeah? And that, by the way, is the same way that we count them in matrices. So how many of you guys have taken or are currently taking 223 linear algebra? Yeah. So it's the same count or same scheme, except because, just to keep things spicy, where do we start counting in computer science? And where do you typically start counting in math? One, right? Other than that, it's basically the same thing. Okay. Okay. So in reality, though, like, so there's a pink box highlighted there. That's one pixel. What data is associated to that one pixel? It's three numbers, okay? And in this case, it happens to be 3 bytes for most simple image specifications. And what are those 3 bytes? The amount of red, the amount of green, and the amount of blue, okay? This, by the way, is the same way that you do colors with the turtle, right? So how many of you guys have started, hopefully you've all started, your cool turtle project? Yeah? And hopefully color made an appearance in your cool turtle project, right? And how did you specify which color to use? There were 2 methods. One is you could actually specify sort of canonical names like red. Okay, how many of you guys use that method? Okay, how many of you guys specified the actual red, green, and blue numbers, or did it in hexadecimal? Nobody? How many of you haven't started that assignment yet? Death. Okay. When is that assignment due? Tonight. Due today, due today. Mark, I regret to inform you that approach is very dangerous and will not work later in the semester. It might work now.
I'll fix it.
You better, or I'm going to fix you. Yeah, okay. I haven't even started to procrastinate yet, right? Okay.
I've been meaning to procrastinate, but never got around to it.
Yeah. Okay, so it's three numbers, red, green, and blue, right? And an image, it's going to store those values in whatever file format. And, you know, what file formats are there, by the way, for this, for images? JPEG, PNG, the one that's GIF, which, how do you pronounce that? Is it a GIF or a GIF?
It's a gym.
I know that this one's maybe more triggering than is a hot dog a sandwich. Okay. Yeah, well, how do you say the name of peanut butter? That's GIF. GIF. Okay. So how do you say the image format? GIF. GIF. Yeah. Yeah. Okay. Anyway, bitmap is another one. TIFF is another one. But JPEGs and GIFs are pretty common. Of course, with GIFs, one of the things that's cool about them that you can do is what? Huh? I couldn't hear that, sorry. Uh, well, they do, but they can also be animated, right? Which is why, like, I mean, how many times have some of you have been the recipient of one of my animated Picard facepalm GIFs as an email response, or on Discord, right? Say when you meme back and forth and have a conversation, right? You can have animated ones. Okay, but anyway, those are sort of the common file formats that we'll deal with, but essentially for our purposes are just red, green, blue pixels. That's it. And the ones that we'll deal with are sort of standard color, meaning that they have color values between 0 and 255 for each pixel. Obviously, if you're doing like really, really high-end photography or something like that, you may need a more robust color profile, but it's essentially the same idea, just bigger numbers. Okay, so what you can do then in terms of image processing, I'll just show you a quick example here, is, well, first off, the colors. Red is, of course, fully red with no green and no blue. What's all zeros correspond to? Black. And what's all 255s correspond to? White. And then other colors are just going to be mixes of however much red, however much green, and however much blue. Here are kind of some of the common, I wouldn't say that, like sort of kind of primary colors, right? Red, green, blue, white, black, yellow, magenta, which is kind of a pinkish color. And you can get lots of other colors by doing sort of more subtle mixes of them. If you want to like get a really specific color, like a specific, like red, for example, right? Wabash red is not 25500. It's a little different than that, right? So how do you get that? Well, one way you could do is just get an image that has Wabash red in it and inspect, like in Photoshop, a particular pixel and see exactly what the color code is there. And then match it precisely to Wabash red. Or, let's say you're making advertisements or something for a company and you want to use their logo and have the text match. Well, you better nail that color because they're not going to pay you otherwise. Okay. Okay, so let's take here let me go down here. Here is a simple image, okay? And at the beginning, next time, I'll show you guys how you can do this not in Runestone, how to do it locally, but that will require installing a couple of packages and stuff. So I'll walk you through how that works next time. But what are we doing? We're going to import this image package. We're going to create a specific image from a source image that would have to be in the same directory as your Python script. It is on the online web thing. And I can, for example, get some information about that particular image. For example, what size is it? It's 400 pixels wide by 244 high. And if I pick some random pixel, I can see how much red, how much green, how much blue is for that pixel. Okay, great, whatever. Now, I can then modify it, okay, by doing something, well, let me just scroll down here, okay. So I can change the pixel's value, okay, to have a new number of red, green, and blue based possibly in some sort of formulaic way on what it was before. Okay, so the example that they use here is, remember that Luther image of the bell? Okay, that's from Luther College, which is where many of the authors of this book are from. So if I run this, what's it going to do? Okay, it's basically going through and negating all of the colors. Okay, and it's doing so by changing its red value from what it was to 255 minus that. And same thing for the green and the blue. And what you get is basically like the photo negative of it, right? So in terms of like old school photography, when you take a picture and you'd have the negatives and then you'd go into the dark room and develop them and there'd be all those nasty chemicals and stuff to get the actual final image, that's essentially what it's doing here, right? Is that negating process. And you could kind of see it was going row by row, right? And it took a few seconds to do it, because each row has how many pixels in it? What was it, like 400 or something, right? So how many times, how many pixels did we have to adjust here? Well, whatever, 400 times, what was the width, 240 something? Yeah. So that product, whatever that is, right, that's a lot of pixels. And we had to modify 3 values for each one. And it was kind of slow. It might be a little bit faster if you run this natively on your computer because it's not running in a web browser or whatever. But we get the idea, right? Okay. So this image package will continue a little bit with it, like you said, on next time. And actually, I guess we do have a few minutes to at least start talking about how to actually import it. But yeah, but what's the salient point as to how we did the manipulation? What did we do? We did some math and we did it inside of a double nested for loop, right? Because I need to do things for rows and for each, and I also have to do things for columns, right? So I'm thinking of this thing as being a group of rows, and then I'm doing something on each row and then moving on to the next row. Okay? Could I have reversed it and thought and worked in columns instead? Yes, that totally works. So that would be switching the row and the column, right? Reversing the order, right? So in fact, let's do that just for sake of demonstration. So, oops, wrong mouse. Let me take this and put him here. And then let me tab this one over. Okay, so now which way is it going to work? Right, left to right instead of top to bottom. Oh, sorry. I have a bad habit of hitting Control S every time I do something and saving it. And when you're in a web browser, you don't want to do that. So yeah, okay, so it moves left to right instead of top to bottom, right? Now, mathematically, is there any reason to do one over the other? Not really. Um, Although it turns out that in terms of how data actually gets stored in memory, there are better ways of doing it. Like one way is faster than another, and it's maybe not obvious that it's that way. But that has to do with how memory is organized in a computer, and for that, take CS-241. We'll talk all about it, okay, later. Okay, good? All right, so the libraries that we need here, and how you install them, okay? So, and it mentions it somewhere in here. Image processing on your own, okay. So if you want to do this same stuff but outside the textbook, we need to install this package called CImage, okay? And you can download it from its GitHub page, or you can just do it as so. In order to install it, though, or a way to install packages is using this program called pip, okay, or pip3 for short. And we also will need to install this package called Pillow if we want to use something other than JPEGs, okay? So we need to install CImage and Pillow, and then those packages may require other packages, but pip will handle all that for us, okay? So I can do this if I go into, well, actually, let me go switch over to the Pi and do it there because I need to do it there anyway. Okay, you can just do this in your terminal. So I'm going to do pip install CImage, or actually, I really should have typed pip3. Okay, and it has installed it, but it also had some requirement of having Pillow, which happened to already be installed here. If it wasn't, though, it would have installed it for you. So I can also do pip3 install Pillow. Okay. Now, the 3 is not required. The reason that I still have a habit of typing 3 is because for a while when Python 3 came out, people were still using Python 2 for a lot of stuff, and it was pretty common to have an installation of both Python 2 and Python 3 on your machine. And how do you specify which version to use? Pip3 was for Python 3, and just plain old pip was for Python 2. For you guys, since you've all basically all installed Python clean now, the 3 is really optional, but yeah. Okay, so we need CImage and we need Pillow. Okay, and that should basically be it. Okay, then, like any other package, we have to import it into our Python script and then use it and look at its documentation to learn how to use it. Okay, so the book obviously has some of the methods listed out for us, but we could also go to the image documentation or CImage documentation and see exactly which methods and what functions are available to us. Okay, and then do cool stuff with it. Okay, so because one of your other assignments is going to be another do cool stuff assignment, but with image processing. Okay, and we'll get to that a little bit later. Yeah, question. Yours isn't working. Okay, now let's see.
So you just have to put the 3.
I guess you did, yeah. And you can upgrade pip.
And
yeah.
Would this be the same way you install like 36?
Yes, if they, well, okay, possibly. If they have, so there's sort of like a database of different Python packages that pip can get to. And if it's in that database where it knows where to get it, then yes. Otherwise, you just have to download that Python package from whoever makes it and import it the same way that you would if you made your own package, right? So pip3 just auto installs it and puts it in sort of a library directory that sort of, you don't see it, but you can always get to it. Yeah, okay, so good question, yes. Yeah, did you do pip or pip3? Really? All right. Oh, yeah, this is a Windows thing. Okay. Basically, the problem is Windows doesn't know where pip is. Let's look at that after, right after. Okay. Any other questions? So Windows issues, not being able to find pip. Yeah. Yeah, sure. All right, but anything before I quit the stream? We good? Okay. I will see you guys on Tuesday. Have a good weekend.